For thousands of years, the question of whether we are alone was purely philosophical. Today, we have moved from simply wondering to actively reading the shadows cast by planets trillions of miles away. The challenge is a matter of contrast. A small, rocky planet is naturally dark, and it orbits a host star that is billions of times brighter, effectively blinding our sensors with its glare. The James Webb Space Telescope provides the hardware to solve this. Its 6.5-meter golden mirror is designed to capture and concentrate light, allowing us to profile the chemical makeup of worlds we cannot see directly. This process relies on transit spectroscopy. When an exoplanet passes in front of its star, a microeclipse, a tiny fraction of that starlight filters through the planet's atmosphere before beginning its long journey toward the telescope's mirrors. Different chemical elements and molecules absorb light at specific, measurable wavelengths. As the starlight passes through the alien air, those chemicals leave their mark by removing specific colors from the light. Astronomers read this spectrum like a cosmic barcode. If a sliver of infrared light is missing from the data, it identifies a specific molecule, such as water vapor or methane, hiding in that distant sky. This gives us a reliable mechanism to chemically reconstruct invisible worlds. We are no longer guessing what exists in the deep. We are measuring it. Finding liquid water is only the first step. To identify a living world, we have to search the air for biosignatures, the chemical exhaust produced by biological organisms. Scientists look for chemical disequilibrium. Certain gases like methane and oxygen naturally react with each other and disappear. They should not exist together unless something is actively pumping them into the atmosphere. On Earth, our atmosphere is rich in both because plants, bacteria, and animals produce them constantly.
Without life, this chemical balance would vanish. Webb recently found a tantalizing signal on K2-18b, a world 120 light-years away. Alongside expected carbon dioxide, researchers detected a faint trace of dimethyl sulfide, or DMS. On our planet, DMS is produced exclusively by marine life, specifically phytoplankton. It is the very molecule that gives the ocean its distinct salty scent. While the signal is preliminary and requires more observation to confirm, it proves that our ability to detect potential biology now extends far beyond our own solar system. But the universe is a master of disguise. Geology and dead chemistry can create false positives, where volcanic activity mimics the gas profile of a living world. Physical barriers also block our view. Thick layers of haze and clouds can act as a blanket, preventing starlight from reaching the lower atmosphere, where biosignatures would be most concentrated. For years, telescopes looking at GJ1214b saw nothing but a flat, featureless line, the signature of an impenetrable fog. It was only when Webb used its mid-infrared instrument that we could pierce through that smog to see the planet's heat and heavy molecules. By utilizing longer wavelengths of light, Webb can bypass these high-altitude hazes, finally mapping the composition of worlds that were previously hidden from us. Smog is only the beginning. Webb is now returning the first interplanetary weather reports, and they reveal environments driven by extreme physics. On the planet 55 Cancri E, the orbit is so tight that the surface temperature reaches thousands of degrees. The atmosphere there isn't air, it's vaporized rock outgassing from a global ocean of magma. Other gas giants feature winds blowing at thousands of miles per hour. Because of the heat, clouds are made of vaporized silicates, which means it rains molten glass, blowing sideways at supersonic speeds. Even rocky planets are at risk. In the TRAPPIST-1 system, violent solar flares from the host star have likely stripped the inner planets of their air entirely, leaving behind barren, irradiated rocks. Isolating a faint chemical signal from a target trillions of miles away, while filtering out the noise of silicate clouds and iron rain, requires a level of technical precision that tests the absolute boundaries of observational science. The airless inner planets of TRAPPIST-1 provide a crucial data point. This evidence acts as a map, allowing astronomers to bypass dead worlds and focus on more promising targets. The search is narrowing to targets like TRAPPIST-1e or Terminator lines on tidally locked planets. These are the narrow twilight bands where temperatures are stable enough for a fragile atmosphere to survive between a frozen night and a scorched day. Webb is the pioneer doing the heavy lifting. It is identifying the most viable targets for the next generation of massive orbital observatories, specifically designed to hunt for life.
The ultimate goal is the discovery of a definitive chemical cocktail: methane, oxygen, and organic molecules existing together on a single world. The moment a biosphere is confirmed, biology moves from an earthbound curiosity to a universal phenomenon. It would prove that the cosmos is not just a collection of rocks and gas, but a system wired for life. Humanity is no longer staring into a sterile void. We are finally learning to translate the language of light, and the universe is beginning to answer.